This meeting is now being recorded.
Okay, everybody, welcome to the monthly Office of Information Management and Analysis webinar. Today's topic is sublateral effects of herbicides and their adjuvants on delta smelt, and the speaker is Mary Stilway. Mary is laboratory manager at the Aquatic Health Program Laboratory. As a staff researcher under the development of anatomy, physiology, and cell biology in the School of Veterinary Medicine at the University of California, Davis, Mary has been investigating aquatic toxicology and ecotoxicology for over 15 years. She received her BA in English at UC Davis, and during this time joined the Aquatic Toxicology Laboratory as a student researcher. Since then, she has worked with 15 freshwater species, including native and non-native copepods, the endangered native fish delta smelt, and have developed standardized aqueous testing protocols. She has previously acted as the quality assurance officer responsible for evaluating quality assurance in the laboratory to ensure compliance with state and federal guidelines, including US EPA. She currently is laboratory manager for the CABA, probably you have to expand this one, CABA section of the Aquatic Health Program, and is obtaining her MSc in the Animal Biology Program at UC Davis. With this brief introduction, I kindly ask Mary to start her presentation. Thank you, Mary, for agreeing to do this presentation.
Thank you, Dewey, for having me. For those in the room, my name is Marie. This is a multi-year study that we have done in conjunction with the Department of Boating and Waterways. It began in 2014-2015 for the biological opinions. We were asked to evaluate the toxicity of herbicides and adjuvants that they were using in their invasive aquatic weed control program to delta smelt. Thank you. So I'll be going over the results of the data. We looked at a number of different species, but today I'm going to be focusing on the sublethal endpoints that we observed with delta smelt. Sorry, I'm using this flicker I'm not super familiar with. So for a little bit of background, invasive aquatic vegetation, there's two specific. So when we first began this program, these programs were actually the water hyacinth control program and the Aggregates control program, and that was in 2014, 2015. And then since then, they've added other aquatic weed species to their programs, so they've changed the names a little bit. As an example, for water hyacinth, in particular, it was introduced from South America over 100 years ago. And it can double in size every 10 days in hot weather, and it can grow into 6 feet deep of depth. And so it's really hard to control in the environment. And so with these species in particular, water hyacinths and in the Aegaria, you can't actually eradicate these species. So Boating and Waterways focuses it as more of a control program to keep it under control so that we can still have our beneficial uses, navigable waters, and then also be concerned about the aquatic other species that are there that these invasive weeds can negatively impact. And then with the Aggregates, that's a submerged aquatic vegetation, so it's kept underneath the water column. And so this was introduced from Brazil over 40 years ago, and this is actually a common aquarium plant. And so that's how they think that this happened to get into the water column, is that people who had their personal aquariums would just dump the water into either outside or into the toilets, and this is how it got into the water column. So Aegaria spreads quickly, often through fragmentation. So if it breaks in the water column, it'll just grow on both ends. And we've got thousands of surface areas that are affected by this particular species. Boating and Waterways works with a number of agencies throughout California and to do the water hyacinth control applications, and is also the lead entity to be in charge of the herbicide use with the submersive aquatic vegetation program. So in terms of treatment, I've updated these slides since the last time I gave this talk. And so in 2017, For the floating invasive control program, we have two different areas. You can't really apply your herbicides to an entire area at the same time. With the death of the plant, you'll have dissolved oxygen issues, and so they do it in areas at a time. And so during areas 2 and 4, which are, you can't hardly see on this map, but it's going to be the red and the green areas. That's between March and November 30th of every year. And then for area 1, which is the big purple area here, it starts from June to November 30th. And so these are limitations that they have to be able to apply when most fish aren't going to be around or during the times where these plants are actively growing. Depending on the mechanisms that the herbicides work on, you want to be able to target particular ages of the plants where it's going to be most effective. And with the submerged control program, that's between March and July of 2017. Those are the optimum times that they can actually apply the herbicides. Sorry, I'm terrible at this. The what?
The arrow on the left one.
No? Okay, so I'll be careful. I don't know what order this is, but in negative impacts of invasive aquatic vegetation, you're going to have reduced water turbidity. You're going to have increased habitat for predatory fish. So the predatory fish are like to hang out in these vegetated areas as opposed to just in the middle of the water column. The plants themselves compete with native phytoplankton that's in the water column, which is bad. You see reduced dissolved oxygen, which is an issue for other organisms. And you also see a higher deposition of organic material in sediment, which is on the bottom, and that's bad for fish spawning because it has a tendency to bury the embryos when they're in the native wild. Okay. So in terms of application rates, when we did the study, the idea of using the herbicide penoxylin was up in the air because it's something that they were interested in using. But since then, penoxylin was taken off the list because they are running into irrigation problems. So in some cases, some of these slides I couldn't read you, so I'm not going to be talking about penoxylin today, but we'll talk about some of the things we looked at. So for the water hyacinth, an example is up top, up here. And so the chemicals that they normally use for the floating invasive control program is glyphosate, 2,4-D, and imizamox. And oftentimes they use a non-ionic surfactant with these for efficacy, and so they usually use the adjuvant aggregates. So that's one of the chemicals that we looked at. And then for the aggregates, the submerged aquatic vegetation control program, currently they're using fluoridone. They have the potential to possibly use imizamox, but when I was updating these slides, this is what they had currently for the 2017 treatment chemicals. And so down below each picture are the application rates that they are going to be using. And so here you can see these are going to be the estimated field concentrations after application. So with the submerged aquatic weeds, these are applied directly into the water column. So they need to maintain a particular concentration for an extended period of time for maximum efficacy. And that's usually fluoridone, and you can see that it's down here, very low with your parts per billion. And then with the glyphosate, the 2,4-D, and the imizamox, you have your applications, and then when you have your field concentrations, it's estimated you're going to get what's called a 20% overspray. So you're going to be in the boat, you're going to be applying these herbicides to the actual plants themselves. You leave a buffer area next to the bank to make sure that you don't hit anything on that end. And then you can assume that of all your spray that's hitting all of your plants, that 20% has the potential to hit water with no plants. And so you do the calculations, and so with the 20% overspray, these are the concentrations that one would expect from the environment when you go collect the water samples. And so you can see the fluoridone is down here, glyphosate closer, 2,4-D, and then with aggregates and competitor, it's a little different because when you add them to your tank mixes, you actually do a percent volume to volume ratio. And it's usually anywhere between 1 and 2.5% of the total volume. So these concentrations are going to be higher than what you're going to see with the herbicides themselves, but that's just the mechanism of the mixing. So in terms of materials and methods, we looked at delta smelt, and we looked at a number of different life stages. We looked at embryos, we looked at newly hatched smelt, so they were hatched from the same batch of embryos, and then we'd give them about 2 to 3 days to kind of acclimate to being alive, and then we'd use them in toxicity tests. And with those early life stages, we looked at survival. We looked at hatching success in the embryo, so did they actually hatch? Did they survive after they hatched? We looked at the length, yolk sac area, and oil globule areas, which I'll get into a little later. We looked at histopathology and gene expression. We also did an adult study where we looked at endocrine disrupting effects, and we'll talk about later in the talk as well. So on those fish, we did histopathology and gene expression. And so we also looked at zooplankton, we looked at copepods, Eurythemora affinis, and for that we just looked at mortality, and we looked at the diatom Thalassiocyra pseudonana. It was a marine species, so we did that a little higher salinity than freshwater to kind of be representative of, further downstream in the delta. And so I'll talk briefly about the zooplankton, the diatom, and as well as the other sublethal endpoints with the smelt. So we'll just go through those, but I'll kind of gloss over the ones that aren't necessarily pertinent for today. So in terms of results, I'm going to go by chemical. Maybe.
Yep.
Keep you on your edge of your seat.
What if you click on the arrow there?
There we go. Okay, great. Thank you. Oh, I had a little bit of a formatting issue on this. Sorry about this. Okay, so in your slide, if you're looking at this line is actually supposed to be down here at the bottom. So this is not going to be entirely representative of field concentrations, for which I apologize. But try and remember what we talked about on the previous slide in terms of the graph you saw earlier. But in terms of fluoridome, so down here at the bottom of the graph, we have all of the endpoints that we looked at. So delta smelt is abbreviated by DS. We looked at mortality, we looked at the larvae mortality, and then we have it right, the OGA is oil globule area, yolk sac area is YSA. We looked at length, and then we also looked at the copepod mortality and then the diatom growth. And because it's an algae, so you look at cell growth. And then with the asterisks, these indicate the lowest significant values that we saw in the testing. And so, and over here on the left-hand side is the concentrations of fluoridome. And so these are in parts per million, which is in milligrams per liter. If you remember from one of the previous slides, a lot of the application concentrations are in the micrograms per liter. So we're talking about orders of magnitude difference here. And you can see that with the hatched embryo yolk sac area and the delta smelt hatched embryo length, we saw significant reductions. And we saw these at around maybe 80 to maybe 10,000 parts per million, so pretty high. And then in terms of the copepod mortality, we saw this around 10 part per million. And then we actually didn't use this chemical when we looked at the diatom. So in instances where we have an NA, for whatever reason we don't have that data point, either it wasn't a point of the contract or it wasn't asked of us to evaluate.
So just so
yes.
I'm clear, top end of the graph is that point at which, that concentration at which you found sublethal effects.
These are the sublethal effects down here. So this
Right.
is where we saw significant, statistically significant differences, yes.
Right. Okay.
Sandy, can you go moving that forward? Can you help us do that?
Oh, okay. That just popped up?
Oh, okay, great. And so this is the concentration that we saw was 15.6 parts per million. So again, much higher than the concentrations used in the field. Right here, 15.6 parts per million. That is the level we saw. Thank you. Sorry for all of this. For amizomod, you can see that, again, the field concentrations are off. But you can see, even with this incorrect field concentration, you can see that the where we saw these effects are still far behind what you're going to find in the field. But again, we saw instances of statistical differences with delta smelt larvae length and copepod mortality. And so the asterisks are supposed to be up here, but they're high. So this is at 100 parts per million, which was the max concentration we tested with this chemical. We ran into some solubility issues. So it's possible that maybe we would have seen effects higher up, but for the study, it was capped at 100 parts per million.
Marie,
so,
were these tests done, laboratory?
These were
so
tested
you weren't taking samples out of the delta itself or anything?
No, and I'm
okay.
sorry, I should explain that. These are all laboratory water, synthetic control water, and it's compared to negative control. And we actually don't have yolk sac area. We didn't have good data for this data point, so I don't have that to show you. You're just going to do it for me? Okay. Oh, yes, and over here with the copepod mortality, that's at 11.4 parts per million. That's the concentration we saw that. And then we saw a negative effect. So by itself, amisomox by itself didn't affect this particular endpoint, but when we saw it in mixture at 500 or 0.5 parts per million, in mixture with a non-ionic surfactant aggregate, we did see a negative effect in this endpoint. And we'll get into talk a little bit later how the differences that we saw between the individual herbicides and then herbicides in mixtures with the non-ionic surfactant. So with glyphosate, we did test this without an adjuvant. That was part of the contract guidelines that we followed. And so this one works. So these are the field concentrations down here. Again, we did not test this chemical with the diatom, so I don't have that data point. But you can see that in the delta smelt hatched embryo yolk sac area, we saw a significant back here, maybe 9,000 parts per million, guesstimated. And then for the copepod mortality, again, saw this. So you'll see that the copepods tend to be a little more sensitive, but again, the concentrations where we saw these effects are still much higher than what you'll find in the environment. For 2,4-D, here is your application, our field concentration, and we saw significant effects in delta smelt hatched embryo yolk sac area. We saw it in the hatched embryo length, and again, copepod mortality. So you can see a trend where the acute effects we're not seeing so much, and what we're really seeing are the sublethal endpoints being affected by these chemicals. And then with aggregates, this is a non-ionic surfactant, and so you can see here in comparison that the field concentrations are higher than in the herbicides, and then we saw effects in more endpoints with this chemical. So we have the oil globule area in the hatched embryos, we have the oil globule area in the larvae, we saw it with the delta smelt length, again with the copepod mortality, and then we also saw it with the diatom growth. And so the concentrations we saw these at, again, pretty high, but 6.4 parts per million for the yolk sac area for the embryos, 8.5 parts per million for the copepods, and then we go up to 30 parts per million for the diatom. And then in competitor, we didn't see any significant effects with the smelt, but the diatom was extremely sensitive to this chemical, and you can see here that this is the only endpoint where we saw that was affected in your field concentrations. But I have to say that with this particular surfactant, it tended to sit on the top of the water column. And so if you consider that these non-ionic surfactants are mixtures of oils, they're not going to mix readily with water. And to a degree, we saw this in aggregates, but I saw it more with competitor, and I think it's the difference between the oils. From what I remember, competitor, and I've got the audience here, so I have to be careful.
It's a vegetable oil.
It's a vegetable oil versus a paraffin, right? Isn't it paraffin?
Petroleum-based.
Yeah, petroleum. So that may account for the differences in sensitivity, or maybe why we saw it floating. But I did know that we did see instances where we saw the competitor on the surface of the water that may have affected the ability to get the dissolved oxygen or have any kind of oxygen exchange, and so that may have been a factor with the sensitivity with the diatom. And so this was extremely relevant at almost 2 parts per billion. So this is an order of magnitude lower than what we're seeing with all of the other endpoints with the other species. Okay, so in talking about, this is kind of like the graph. From this point, we're going to look more at the sublethal endpoints, so the yolk sac area, the oil globule. We'll go into more detail here. And so these are some photos of the fish. So in order to determine length, we actually took photos of all the fish after we euthanized them, we preserved them, and then we used a program called ImageJ where you're able to take your micrographs and you're able to measure them to get length based off of pixels. And so we used these analyses. So these are the microgram pictures of the smelt. And so in the top picture, these are embryos. So these are from the embryo test that we used that hatched out. And so after the end of the test, we preserved them. And these were the status of the animals after they hatched. And so up here, these are animals that were exposed to 250 parts per million of fluoridone. In B, you see it's 2,500 parts per million of the glyphosate. Down here, this is 2,4-D, and this is at 1,000 parts per million. And then down here is misomox, and it's at 50 milligrams per liter, so 50 parts per million. It's at a lower concentration. And so when you're talking about fish, this is what a fish is supposed to look like when it's healthy and normal. So you have a straight spine, you have your yolk sac area, you have your oil globule here, here's your eye, and then this is what a fish is supposed to look like. So if you take a look at the fish exposed to a misomox and then the fish exposed to the glyphosate, they match what you're seeing here. When you look at fluoridone and you look at 2,4-D, you seem to see morphological deformities causing them to have curved spines, which is an issue in the wild. In terms of an embryo, this is what a normal embryo looks like. So as the fish is developing, it's transparent, you can see it, and so ideally what you'll have is the fish that's turned around. Here's their oil globule and the yolk sac. And I should say that for the newly hatched smelt, when we tested them in the laboratory, they actually didn't have their mouths developed yet, and so they survived solely on their yolk sac area and their oil globule through nutrition. And so during the course of the test, we didn't feed them. And so that's kind of an indicator of nutritional status. And then in the embryos, you can see that they've developed in the embryo, and then when they hatch, they haven't had a whole lot of time to use their natural resources in terms of nutrition. And so these are an indicator of how your animal is developing, whether or not these are in the areas they're supposed to be. And so where we saw significant differences, so this is an example where we saw a significant difference. We saw the yolk sac area was smaller than what we saw in the control in these hatched embryos, okay? So that means that it is being used faster than it should be. So maybe there's an elevated energy resource that's being used at development that is higher than it should be. In terms of the animals that were exposed to glyphosate, we saw yolk sac morphological deformities. So you can see here that the oil globule and the yolk sac is kind of just no longer defined between the two of them. So I don't know, and I don't have an example, I don't have a reason of how this happened or why it happened. I'm presuming it's because of the exposure, but these are things we saw, and this would not allow the fish to use it. If your oil globule and your yolk sac are all kind of no longer separate entities, then you can infer that maybe the fish would not have the appropriate mechanism to be able to use it because they're deformed. And then in some cases, when we saw it with the 2,4-D, we didn't even have an oil globule. So, I mean, it was missing entirely. Whether or not it was used in embryonic development or it just was never there to be as an offset is a problem. And then here's an example that is not significant. So it's normal usage in these fish. They all look fine for the most part. So it's not that picture. But as a comparison, you can see the differences. So this is what I'm talking about when we have, when you see a bunch of graphs, you see a lot of asterisks. But this is what it means visually, and this is what you can see what the fish are actually experiencing in the wild if they're being exposed to these concentrations, I have to say. Yes.
What was the duration of the test?
For the embryo test, they were about 11 days, and we put them in the next day after they were fertilized, and we allowed them to hatch, and that ranged anywhere from 9 to 11 days. And then for the larvae, it was 7-day to 8-day test, and, sorry, I should have said this earlier. We had a 4-day chemical exposure, and then after the 4 days, we moved them into clean water, and then allowed them to hatch or allowed them to grow to see if there was any recovery. And so, also what we saw in addition to some of the sublethal endpoints, we saw these morphological deformities. So again, we've got curved spines here. In the tests themselves, what they would do is they would just swim around in circles like this. So their spines were curved to the point where they just really had no other option. So they were able to swim and they were alive, but they were swimming around in circles, and in the wild, that's something that you would consider maybe ecologically dead, in that if you have an animal that's just swimming around in circles, they're going to have a higher predation rate, they're going to be unable to forage, they're not going to be able to move around, and gain any ground. So even though they're still alive, it's noteworthy in that these would not actually survive if we put them into the wild. We saw this again in 2,4-D, the curved spines here, and we did see some recovery periods with some of these chemicals. Not so much with fluoridone, but with glyphosate and 2,4-D, we would see these morphological deformities, and the fish would be swimming around in circles, or they'd be really disoriented when they were in the 4-day chemical exposure portion of the study. But then when you moved them into clean water and you gave them about 24 to 72 hours of clean water, they actually kind of got over it. And so you saw instances where maybe they looked like this in the beginning, but then by the end of the test, they exhibited more of your typical morphological So that's something interesting that we saw. So considering that these are being applied in a certain amount of time, and that with the water moving through, it's possible that maybe these fish would be exposed to this detrimental level, but then would have the chance to recover in the wild, assuming they don't get eaten first in the timeline. And so this is something that we saw, and this is actually at a more environmentally relevant concentration. So from the earlier slides with the ammonium, we had concentrations of application anywhere between 1 and 11 micrograms per liter. And so here it is at 12 micrograms per liter. So just a smidge higher than what you would expect to see in the water column, and then this is the concentration of aggregates that we were able to calculate based off of that 1 to 2% ratio. So it ended up being 113 micrograms per liter of the aggregate. And so we saw this in a number of cases where a misomox by itself, we didn't see any negative effects. In some cases, an aggregate by itself, we didn't see any effects. Just put them together, and we saw negative effects. And so as a comparison, so here's the control fish, and this is all normal looking. So here's the heart. So this is like the heart area right here. It's kind of hard to see. This in particular is the atrium. This right here is the ventricle. Right here, this is the aorta. So you can see that there's plenty of tissue here available. There's plenty of area, and then everything can move well in terms of blood flow. Now you take a look at one of the fish that's exposed to 12 parts per billion of the misomox and the aggregates combination, and what we see is pericardial edema. And so here you've got a swollen atrium in comparison. We've got edema in the pericardial cavity, so it's swollen and large. And so here it is on like a whole fish. So this is the section. These are histology slides. And so here's the section of the fish. This is the eye. Here's the mouth. This is the heart area right here. And so here is your atrium, and then here's your cavity. So you can see how it's really swollen. Really, I mean, there's no really other word for it. And as a closer look up, you can see all this area. And you can see the difference too, where you can have all this tissue, all this purple, that stain. This is good. And you can see a distinct difference in all of this. So this is a significant issue that may be occurring when these fish happen to be in the area when you have these application rates. These were seen in the larvae. These are from the larvae test, the hatch larvae test. And so this is one of the things we saw for histopathology. Yes.
What is the frequency of that in the test that you saw? How often did you find that?
I want to say this is the concentration we saw it in. I'd have to go back and see because I didn't personally process this part of the data, but I could double check the frequency of that. But enough to make it onto the slide. So it wasn't just a one-time thing we saw it here and there. It wasn't an outlier. It was something that we saw consistently in those test treatments at those concentrations. In the same concentration, we also saw skeletal muscle necrosis. And so this is a section of the skeletal muscle. And so here's the control, and you can see all the striations here that are very nice and smooth. You've got your cells, dark circles right here. Those are all very nice. And then you have the skeleton in the middle. And then in the same, well, this is slightly different. In some cases, we did 12, we did 11. It just kind of depended on the test. And so here you can see a significant difference in terms of what this skeletal muscle looks like in the fish. And so here you've got, it's not serrated, it's kind of all over the place. We have these vacuoles of emptiness. That's not good. It's just nothing. And so you can expect to see something like this, and this may have been contributing, to some sort of lesser morphological deformity. So in the fluorodone and in the 2,4-D, you saw them where they're certainly curved. And so that's where you're going to see an issue. We didn't see that in the amisomox, but it's possible that maybe they just didn't grow well enough, and that's why you didn't see those curvatures. But there are still things happening that can be negatively interpreted as a potential problem. And again, this is at an environmentally relevant concentration. Okay. And so going into the adult delta smelt test, we did this on sexually mature adult delta smelt. We conducted this at SWCL, so that's the Fish Conservation and Culture Laboratory. So that is the hatchery that supplied all the delta smelt for us for the testing. And they do a lot of research, and so we did test with this. And so, we should do one before that, maybe? No? Okay, well, I had to slide in between this. But in terms of materials and methods, it's down here. We had 5 each of male and female, so we could discern gender differences because it's an endocrine disruption test. It was a 6-hour exposure, so we exposed the fish for 6 hours in the chemical treatment. After the 6 hours, we took them out, we preserved them, dissected them, and then we ran analyses on them. And so we looked at fluorodone, penoxylum, amisomox, and glyphosate for this endpoint, although I won't be talking about penoxylum today. And so this is a picture of how the test treatments look. So we just used black buckets, and we had temperature controlled, and let's call it like a water bath, where we had circulating water to keep it at the optimum temperature. In these laboratory tests, you want to make sure that all the physiological parameters are ideal for your organisms. That way you don't have any confounding variables, like maybe the temperature is off, and that's why we saw a bad result. So this was kept at the optimum temperature. This is an example of fish that we saw after the 6 hours, and these fish were exposed to fluorodone. So, yes?
These are static type tests, like we dose the
These are static tests, yes.
Okay. So
well, they were actually all static tests. They were stat for renewal. So we
Hydrostatic renewal.
yeah, so we changed the water every other day in the early life stage test.
All right.
And then with this one, since it's just a 6-hour study, we dosed it one time.
With the idea of keeping the concentration at that continuous.
Yes. So when we renewed the water, we make sure we match the concentration of everything coming in so that they have fresh.
So in essence, what you get is like, if it's an 8-day test, you get 8 days at that concentration.
Yes. I mean, assuming that the compound doesn't break down in between.
Yeah.
I mean, there's always a little degradation you have to worry about. But the goal is, yes, that maintain that same concentration until we move them into the thin water.
And you use that, the concentrations you're talking about are the nominal values that your target values, but you didn't measure the concentrations over time.
We do have that data. We measured them. I didn't present it here, but we did day 0, and then as the test went to see how much the concentration was. So.
I sometimes repeat the question so that it's about on the phone.
I'll do that. Thank you. So here we saw, in these graphs, we've got the female fish over here and the male fish over here, and these are results for the female and the male, and so these are all fluoridone. So down here are the concentrations of fluoridone, and on the side, we measured glutathione and estradiol in these tests. And so glutathione is involved in antioxidant and metabolism mechanisms, and so it works on detoxification. So if these are impaired, it means the fish can't detoxify itself when it's being exposed to these chemicals. And so, next slide, please. We saw significant effects with the male fish exposed to fluoridone. We saw significant reductions in glutathione in these concentrations. And in the female fish as well as the male fish, we saw significant increases, this is estradiol down here. We saw actually significant increases in this mechanism in the female and the male fish. And so estradiol is generally found in female fish. So when you have something like this happening in the female fish, you see it, something you would expect. But because it was significantly increased compared to the control, it means it's producing more estradiol than it should be in this case. And then with the male, regulators shouldn't be producing it at all. Estradiol is a precursor for making yolk for eggs. And so when you see estradiol induction in male fish, I mean, you can have the possibility that maybe it's going to start producing vitellogenin or farinogen, and those are both like the preliminary steps of forming eggs. And so that's an instance where you have the potential to see intersex happen in your fish because these male fish are producing enzymes and they're producing things that should not be taking place in the beginning.
These are environmentally relevant concentrations, I can't see.
This is at 100.01 milligrams per liter, so probably higher than what you see in the environment, but a little lower than the concentrations that we tested with the early life stage. We went super high to see that. But with these guys, it's a little more representative of it, but still higher than you're going to see in the environment. And so we did the same thing. We looked at acetylcholinesterase. And so acetylcholinesterase is an enzyme that catalyzes the breakdown of acetylcholine, and so it's used in functions of neurotransmitters. And so when you see either inhibitions or inductions of them, that's going to affect whether or not the fish can move, because you'll find them in like skeletal muscle. And so what you see a lot of times is that if they have like an influx of it, they kind of twitch around, they can't swim. So this is going to have applications in the wild where it may affect their ability, again, predation, foraging, that sort of thing. And so again, we did same test procedures, 5 fish, 5 male, 5 female, 6 hours. And so here is the female result, and here's the male. Misomox is down below on the bottom, and so this is the acetylcholinesterase concentrations that we saw in these fish at the time. And so we saw significant reductions in, there we go, all of them in the females, and in the lowest and the highest concentrations in the male. So this could potentially be a problem because it's telling you that in all the concentrations tested with the misomox, you have the potential to have neurons affected, synapses. We didn't see this translated in acute responses, but the potential exists, so you can't necessarily rule it out. And what's noteworthy with the misomox, you see it in the lowest concentration and the highest concentration. And this isn't my data, so I can't extrapolate too much, but the fact that it happened in the lowest concentration, it can be cause for concern because it's going to be lower and closer to environmentally relevant. And these are going to be in parts per million, so this is 0.011, so I think this is like 111 parts per billion, I think, maybe. without having a calculator. So that's actually kind of close to being environmentally relevant. So what does this mean in terms of implications? There was a lot of data that we looked at. There was a ton of endpoints. There was a lot of species. Generally speaking, we saw very little to no toxicity in the acute endpoints, and I think that's really important to keep in mind. With the early life stages, delta smelt with the individual herbicides alone. So that's good. But for the most part, especially with the floating aquatic vegetation control program, those are often used in conjunction with an adjuvant. And so when we saw it in combination, what we found is that there was a substantial risk increase when it was in mixture, because that's where we started to see the environmentally relevant negative effects. And there's a lot of data in the literature that says that you'll see these kind of synergistic effects in mixtures, especially with non-ionic surfactants in the wild, not in the wild, but in laboratory tests. You'll find that the herbicides themselves are relatively innocuous, and the adjuvants alone are relatively innocuous. They tend to have lower toxicity values sometimes, depending on what you're looking at, but when you put them together, there's the potential for synergism and other kind of mixture interactions that can have lasting effects in the environment. In terms of endocrine disruptor effects with the mature delta smelt, there is potential to have that, and so that shouldn't be overlooked either. But all that being said, many of these effects were observed higher than the application rate, with the exception of the diacom that we saw with the competitor, and with the exception of the mixture interactions that we saw with the yolk sac area with the misomox and aggregates. To put it in perspective, these are the aquatic life benchmarks that I pulled off the EPA website in terms of the chemicals that were available. So the non-ionic surfactants were not in that database, so I don't have comparative data to give you. But you can see here that for the ones that I could find, your aquatic life benchmarks, these are in parts per billion. These are all relatively high. They're lower than the concentrations that I tested, but the results that we saw and the effects that we saw were higher than these benchmarks. So there's an adequate margin of safety for most of these chemicals, with the exception of maybe fluoridone. Fluoridone, they have a chronic endpoint of 480 micrograms per liter, which I think is, it's low compared to everything else that you're seeing when you're looking at, orders of magnitude. But when you consider application rates, fluoridone's not really in the water at that concentration. So there isn't a marginal safety, but it should be noted that this is the slowest one that I've seen, with the exception of a misomox, and this is non-vascular plants. I just, abbreviated that. But you would expect an herbicide to work to a certain degree on plants, so that's not entirely surprising. But if you look at all the data, 480 micrograms per liter is a little concerning. But that being said, we didn't see negative effects at that concentration. So something to keep in mind. And then in terms of everything else, for the most part, it looks like we have a fairly relatively good margin of safety. So with all that, controlling these plants is a very big responsibility that has to get done. And so at this point in time, it looks like the herbicide control is the most effective. And with the results that we've set here, so far what we've seen, the safety factor margin is adequate for use of these chemicals. So in terms of acknowledgements, there was a lot of people who worked on this project, and a lot of man hours were spent. Boating and Waterways was really great in terms of being helpful and providing everything that we needed. U.S. Fish and Wildlife Services was integral in helping us with some of the project design. We got a lot of our herbicides from CPRO, and they were very kind to give them to us, and they also ran a lot of the chemical analysis as in-kind services for this project, which was really helpful. Dr. Hung from FCCL was kind enough to provide the testing space for the adult smelt test, as well as providing all of the embryos and all the hatchlings that we did use for all of this. Krista Hoffman was great. This was part of her PhD project in the early stages, and so I'm presenting part of her data as well as this. And then everybody who worked on all of the endpoints. It was a very big group effort, and so we wouldn't have been able to finish it without everybody working together. So technical difficulties aside, if there's any questions, if we have time for that.
Yeah, we have few minutes for that. So we'll give chance for people on the phone. We will unmute you now. You can go ahead and ask. In the meantime, you also ask.
Yes, I saw your hand first. I'm sorry.
All guests have been unmuted.
I don't know where to go. Okay.
Yeah, my question is your data for laboratory quality. Your fish might be stressed as a multiple factor by confounding your toxicity. Sensitivity might change in the wild condition.
Yes.
You see what I'm saying?
Yes, that's
so
very
then
true.
your conclusion might be cautious. So because don't have correlation with wild.
That's very true. And there's going to be a lot of differences. I mean, this was in a laboratory setting. Make sure everything was optimum for them at the time. We used a synthetic control water. I mean, this is not in a matrix. That's something that I've been really interested in looking at this in the actual ambient matrix effects we're seeing.
Right.
Because these herbicides are not the only chemicals that are going to be in the water column.
Right.
And so this is just they've isolated in a laboratory setting.
Right.
You're correct.
So your sensitivity will change, then your conclusion will change.
Yes, that is entirely possible. But as a working conclusion, based off of what I've done in the lab, is what I think we can infer from this. But that's a very good point.
Okay.
It's time for
One on the.
Okay. Computer question?
Yeah. How do you explain the lack of a standard dose response for many of the endpoints and chemicals?
Ooh, that's a very good question. In terms of a lack of the standard dose response, if you mean in terms of increasing response to increasing dose, we didn't see that a lot. A lot of times we didn't see an increasing response. We didn't see a response at all. So that's encouraging. In terms of seeing something that didn't fall under your normal S-curve that you would expect, I can't necessarily say. In some cases where you see stressed animals maybe in the lower concentrations without a corresponding high concentration, we were thinking that maybe that might have something to do with hormesis. Hormesis is a concept in toxicology where, briefly paraphrased, low levels of stress can actually be good for you. And if you are under at least a little bit of stress, you're going to perform a little higher, and so you may not see these things. So that's one aspect we were considering that might have played a part in this, but outside of those two theories, I don't have a more definitive answer. You had a question? Yes.
Just a point of clarification.
Yes.
Aggregates and competitor are not non-ionic surfactants. They contain non-ionic surfactants.
So then how would you categorize them?
Typically, aggregates would be characterized as a crop oil concentrate.
Okay.
And it would typically have 15 to 17% by weight of the product would be the NIS surfactant. The rest would be petroleum oil.
Okay.
With competitor, it's about 25% would be an NIS, and the rest would be the vegetable oil component or ethylated seed oil.
That's really good to know.
So it'd really be better to refer to them as crop oil concentrate rather than an NIS. And that's my other question. My other question is, it seems like the choices here of those two are old, last century choices. There's been a lot more research done and a lot more modern adjuvants that would have better toxicological responses that are approved for aquatic use and much softer chemistries now available for this potential purpose. So how would one go about getting those tested or into the system to be evaluated for this use? Some of the interactions too, I deal with it. I'm the formulation chemist for Wilbrellis for adjuvants, and your point was well taken that the interaction between the two chemistries is going to have a different toxicological response. That's exactly why you sell an adjuvant with a herbicide, so it would make sense that would be true of Smelt and other things as well. But that same interaction, we see differences in some of the new different chemistries now, where you don't see that same sort of response. Rather, we're trying to get the best possible efficacy without having off-target phytotoxicity, where we're negatively impacting the crops we're spraying on, for instance. So I would encourage you to try the department to try to look at more modern technology for adjuvants to boost the efficacy of the pesticide itself and while reducing the concentration.
Okay, we'll start at the beginning. See me afterwards because I need to write all that down about your adjuvants because that's important, and I've been calling it non-ionic surfactant, so I want to change that in all of my future talks. Second, I was contracted to do this work, so I'm not the decision maker. My guess would be you would want to contact Coding and Waterways and discuss the options with them in terms of changing the types of adjuvants they could possibly use in these control programs. That being said, they have a lot of regulations. They have biological assessments, biological opinions. Those are all on their own individual and oftentimes need to be finalized prior to them even being able to use these new products. So that might be possible in the future, but I don't think that would be an immediate thing we could do. But it's worth looking into because I agree that it would be in everyone's best interest to try and find effective type of mechanisms to control the organisms and plants, in addition to making sure that all of your non-target organisms have an adequate level of protection while we're working with these control programs. So I think it's great that Wilbur-Everest is taking the steps to make greener products in order to meet exactly
I'd like to talk to you about that after.
Can I ask another question?
Yes.
When we qualify adjuvants for use and can get a for aquatic use label, the thresholds that they use for the testing are 10 parts per million, 10 parts per million for brook trout, and 1 part per million for daphnia. Does that correlate fairly well with what you would see for your responses? And why would you use diatoms versus daphnia, or it strikes me as odd that there wouldn't be some commonality. Here we're getting approved using daphnia, and you're not testing daphnia.
Well, this is a research study, so we used a little bit of different organisms. We wanted to be specific to the delta. So copepods are in the delta. They are a food source for the delta smelt, and so in this case it made sense to use those in conjunction together. With the choice of the diatom, it was something that was not necessarily readily available, even though it is a standardized testing species, but we thought, again, it would be more applicable to the delta itself. With the EPA registration data, those are surrogate species that can be used across the way, and so you'll see things like daphnia, brook trout, fathead minnows, and you're going to see different sensitivities based off the organisms themselves. So it does make sense that you would use something like 10 parts per million. You say 10 parts per million for the brook trout, and you did 1 part per million for the daphnia. Because
and it's fingerlings. It's fingerlings.
Fingerlings, okay. So they're going to have different sensitivities for seeing different organisms together, so that would make sense. In terms of being registered for aquatic use, it just depends on the end goal. So the registration data is used in order to get it out there so they can be used, and that's federal registration data. Then you have the next steps of trying to register it with individual states. In some states, you can get it in easier than you can. New York and California are two of the states that are the hardest to get registration data approved to be used in these two states. So there's a little bit of jump around you have to do.
Washington.
Yeah, I want to give opportunity for the people on the phone. Is there more questions from the phone?
Yeah, can I ask a question real quick?
Yeah, go ahead.
Yeah, were you monitoring other water quality parameters, pH, dissolved oxygen, or conductivity throughout the treatments?
Yes, we did all of those, and with the glyphosate in particular, we ended up having to pH adjust samples back to the normal ranges because of the concentrations that we tested the glyphosate made it super acidic. So we ended up having to adjust back into the 6 to 9 range, and I also included an additional pH adjusted control for any kind of differences we may have seen due to the pH shifting themselves. But all of the other
that was going to be my next question.
Oh, okay, great. Well, great.
So more questions from the phone?
Just to follow up on that, you didn't have to do any aeration in any of the treatments. There was no biochemical oxygen demand issues?
No, actually, we didn't do any aeration, aside from maybe the theory with the diatom and the competitor, where we may have had some dissolved oxygen issues from there. We did see lower values at the end of that test, but by nature of the algae test, it's a static test, and we don't touch it between when we set it up and take it down. So in terms of an application of an aeration, I don't know if that would be possible. It may be, but only because I've never personally run into that problem with an algae test.
Okay. We will take one more question. This is supposed to be a 30 minutes webinar today. We kind of extended.
I'm sorry.
Yeah, that's fine. But if there is one more question, we'll take that one and we'll close it.
What is the next? I have a question. So are there any proposals for further study or recommendations for further study?
We just finished a study with William Waterways where we looked at a number of other herbicides in kind of future biological opinions on something they may be able to do. So we have some testing on that unfortunately I can't discuss at this time because I just gave them the data. And then I'm always interested in doing future studies. So if anybody has funding opportunities that they would like to share with me, I would be more than happy to discuss project ideas because I have a lot of them. But number one, though, is I want to get out to the field and I want to look at this in an ambient matrix because I think that's the one big question that everybody has. And I think that's the biggest difference between what you're going to see in a lab under ideal circumstances and then what you're going to find relative to the field. And then maybe some in situ testing I think would be super cool as well, but I think that's a couple years down the line.
Okay. Thank you, Mari. Thank you, everybody, for participating. We'll see you in the next seminar.
Thank you so much. So far, I went.
The host has left the meeting. So at this time, the meeting will come to an end. Thank you and goodbye.